we were discussing the problem on finding the eigenstates and eigenvalues of the operators j square and jz. In the first part of this lecture, you have seen some of the important calculation regarding this problem, and in this second part of the problem, we will actually complete the calculation of eigenvalues and eigenstate of the operators j square and jz. So first of all, I would like to just repeat the important results which we have discussed in the first part of this lecture. You have seen that we have written the eigenvalue equation for the operator jz like this: jz operated on ket psi equal to b ket psi. You know, here the ket psi is the eigenvector or eigenfunction or eigenstate of the operator jz, and we have assumed that this b is the eigenvalue of this operator. And when we have considered the repeated operation of the raising and lowering operator on this eigenstate ket psi, then you have seen when we consider that j plus minus to the power n ket psi is the eigenstate of the operator jz, then we have found that the eigenvalue of this operator jz is equal to b plus minus nh bar. In fact, when you will take plus sign, that is raising operator, then the eigenvalue will be b plus nh bar, and when you take the lowering operator j minus to the power n, then you find that the eigenvalue of this operator is b minus nh bar. And in this way, we have obtained the two important equations for the minimum and maximum value of the two numbers k and l, and those equations were jz operated on j plus l plus 1 ket psi was equal to 0, and jz j minus k plus 1 ket psi equal to 0, which I have written in this equation A4. Here actually k is the minimum value of jz and l is its maximum value. And in the light of these two equations, we have obtained that the eigenvalues of the operators jz are restricted between two values, two finite values you can say, although according to this result defined in equation 2, the eigenvalue of the operator jz will be from minus infinity to plus infinity, but in practice it is restricted between two finite values, and those finite values we have obtained in the previous lecture like this. This was the least value was b minus kh cross, and the highest value was b plus lh cross, where k is the minimum value of jz and l is the maximum value. Now in this second part of the lecture, we will finally found the eigenvalues of the operator jz and j square. So first of all, let us see how we can find the eigenvalues of the operator j square. You have also written the eigenvalue equation for the operator j square in the previous lecture, and you have seen that the eigenvalue equation of operator j square we have written like this: j square operated on ket psi is equal to a ket psi, where we have assumed that this a is fixed and it is the eigenvalue of the operator j square. Now actually to get the eigenvalues of the operators j square and jz, we will see again the effect of the raising and lowering operators. And you know, you have studied in the previous lecture these two operators, that is the raising operator and lowering operator, so you know about it. You know that how these two operators are defined. You have seen that the raising operator j plus is defined like this: this is jx plus ijy, and the lowering operator j minus is defined like this: j minus equal to jx minus ijy. Now from these two equations, we will first of all find the operator j minus j plus. Remember this step because this will be needed for finding the eigenvalues of the operator j square. So let us just put the values of these two operators, that is j minus, you know, this is jx minus ijy, and j plus, this is simply jx plus ijy. Now jx operated on jx, that will be simply jx square, and minus ijy times ijy, that will be plus jy square, because I square will be minus 1, so this will be plus jy square. Now this is jx times ijy, so this will be ijxjy, and minus ijy jx. So I have taken here this I as a common factor, and the remaining terms are jxjy minus jy jx. Now you know this jxjy minus jy jx, this is nothing, this is simply the commutator of jx and jy. So this factor has been replaced by commutator of jx and jy, and the remaining two terms are at each, that is jx square plus jy square. Now you have seen in the previous lecture that the commutator jx jy is simply equal to I h bar jz. So this I square will be now minus 1, so this result becomes jx square plus jy square minus h bar jz. So you can see that we have obtained this j minus j plus operator is equal to jx square plus jy square minus h bar jz. So from here you can see this jx square plus jy square will be what? This will be j minus j plus h bar jz. Now we know that j square operator is equal to jx square plus jy square plus jz square. But this jx square plus jy square we have obtained, this is equal to this much. So replace this jx square plus jy square by this factor. You can see this will be j minus j plus h bar jz, and this jz square is at it, as you can see here. In the similar manner, you can see when we will obtain the value of the operator j plus times j minus instead of this j minus j plus, then you will see that this j square will be equal to j plus j minus h bar jz plus jz square. I have not calculated this, but on the same line, instead of calculating this j minus j plus, you should calculate j plus j minus, and then you will see that your result will be like this: j square equal to j plus j minus h bar jz plus jz square. Simply here there will be just the reverse operators, j plus j minus in the first term, and the second term will be actually minus here, and jz square will remain same. So in this way we have obtained the j square operator in terms of the lowering operator and the raising operator, and also in terms of jz. You can see. Now we are in a stage how to find the eigenvalues of the operators j square in terms of jz. Now you know that the operator j square and jz commute. You have seen in the earlier lecture this fact. And when you say that these two operators commute, it means the commutator of j square and jz vanishes. This is equal to 0. And you know, if these two operators commute, then definitely these two operators have the same eigenstate, or the same eigenfunction, or the eigenvector. So this implies j square and jz will have the same eigenstate because both of these two operators commute. So if you consider that the function j plus L, where L is an integer, k psi, this is an eigenstate of the operator jz, then this will be also the eigenstate of the operator j square. So if j plus L k psi is an eigenstate of jz, then it will be also an eigenstate of j square because these two operators commute. And so let us write the eigenvalue equation of this operator j square, taking this j plus L k psi as a eigenvector or eigenfunction. Therefore, we can write j square operated on the eigenfunction j plus L k psi. Remember, here eigenfunction is not k psi, but we have considered that this j plus L k psi is the eigenfunction or eigenstate of this operator j square. And what will be this? You have seen that this j plus L is equal to, this j square is equal to what? You can see, you have obtained that this j square operator is equal to this much, which I have defined in this equation 1. So instead of the operator j square, now we can put this j minus j plus h bar jz plus jz square. So you can write like this. This is jz square plus j minus j plus h bar jz. This I have written instead of this j square, and the eigenstate is j plus L k psi. Now simplify this RHS a little bit. You can see this can be written as jz square j plus L k psi plus j minus j plus L k psi and plus h bar jz j plus L k psi. You can write it. And this can be written as jz j plus L k psi. In fact, here I have written jz instead of this jz square, and plus, now you can see this j plus times j plus L. This can be written as j minus j plus L plus 1 k psi and plus h bar jz j plus L k psi. Now here we will make the use of the result which we have obtained in the previous lecture. You can see that in accordance with equation A2 which we have obtained in the previous lecture, that this jz j plus n ket psi is equal to b plus n h bar j plus n ket psi. I have not pronounced this minus because here we need only plus sign. So instead of this n here there is actually L. So we will make the use of this equation A2. And along with this we will also use this result defined in equation A4, that is jz j plus L plus 1 ket psi. This is simply equal to 0. So let us make the use of those two results here. So using the results in which equation? A2 and A4. A2 and A4. We get what you will get, you can see easily. This j square operated on j plus L ket psi is equal to, you can see here this is jz and jz j plus L ket psi. This will be equal to what? On the basis of equation A2, you can write this as, this is B plus LH cross J plus L ket psi. Here we have made the use of this equation A2 and plus, now see, J plus L plus 1 ket psi. You can see here this result is actually equal to 0. So the second term in this equation becomes 0 and plus again here you can see that this J plus L kits JZ operated on J plus L ket psi. By the use of equation A2, we will again write it like this. This is H bar times B plus LH cross J plus L ket psi. So making the use of equation A2 and A4, you have seen, you can see this result is obtained. In fact, here in second term we have used the equation A4, and in this first term and in the last term you have used the equation A2. So you can see this. Now again this is just a constant factor. So again you can see that this jz is operated again on this eigenfunction j plus L. So again by the use of equation A2 you can write this like this. This is equal to what? This will be again B plus LH cross times B plus LH cross, and the eigenfunction is J plus L ket psi, and plus this is H cross times B plus LH cross J plus L ket psi. So finally we can write this result in this way. This is B plus LH cross times B plus LH cross and plus H cross B plus LH cross and times J plus L ket psi. So in the terms inside this square bracket, this B plus LH cross may be taken as a common factor, and so this result can be finally written like this. This is J square operated on J plus L ket psi, and this is equal to what? This will be B plus LH cross. This has been taken as a common factor, and this will be B plus LH cross plus H cross You can see here this B plus LH cross has been taken as a common factor, so the remaining terms are B plus LH cross plus LH cross, and the eigenvector is here J plus L ket psi. So what will be the equation number? Actually, you should write it equation 3. So you can see here this J plus L ket psi, this is actually the eigenvector or eigenstate of this operator J square, and this factor is actually the eigenvalues of this operator J square, and this is again the eigenstate. So this equation actually gives the eigenvalues for the operator J square when the eigenstate is J plus L ket psi. In fact, in the similar manner, you can again find the eigenvalues of this operator by taking the maximum value of Jz, that is using this result which actually we have obtained earlier, this equation. By the use of this equation, we can again find the eigenvalues of the same operator J square. So again you can say J square operated on J minus K ket psi. What will be this? Now here we will use the meaning of this J square operator defined in this equation 2. You can see here, because when we will consider the integer k, it means we are talking about the maximum value, and then you should replace J square by this equation 2. So instead of J square, now we will write J plus J minus H bar Jz plus Jz square. So making the meaning of J square defined earlier, which you have just seen, you can write like this. This is Jz square plus J plus J minus H bar Jz. And the eigenvector is J minus K ket psi. In fact, in the similar manner, you will operate this operator Jz square on this. Then again we will operate this J plus J minus on this eigenvector. And finally we will operate this minus H bar Jz on this. And in the similar manner, by the use of the above equations which you have just seen here in this calculation, you can find the eigenvalues of J square in terms of K. But here I am not doing all the algebra. This is just a homework for you. You can do yourself in the light of the above calculation. So here I am just writing the eigenvalues of these operators operated on this eigenvector directly. So doing the almost all algebra, you will find that this result is like this. This is b minus kh bar whole square plus 0 and minus h bar times b minus kh bar j minus k ket psi. I have directly written. You can see this result. This is b plus lh bar whole square plus this much, plus h bar this much. So here instead of plus sign there will be minus, because this term h bar jz is minus, and L has been replaced by minus k. So you can do the algebra in the light of the above calculation. So finally we can take again this b minus kh cross as a common factor, and when you will take b minus kh prime as a common factor, what will be the result? Here there will be again b minus kh prime, and in the last term there will be minus h bar, and this eigenvector j minus k ket psi. So here you can say that this j square j minus k ket psi is equal to this much. Let us say this is equation 4. Now you can see this equation is nothing. This is simply the eigenvalue equation of the same operator j square. Here this j minus k is what? This is actually the eigenstate of this operator j square, and these are actually the eigenvalues of the operator j square, but the eigenstate is now j minus k ket psi. So you can see that we have obtained the eigenvalues of the operator j square in equation 3 and in equation 4 too. In equation 3, the eigenvalues of operator j square is b plus lh bar times b plus lh bar plus h bar, but in equation 4, the eigenvalues of j square is b minus kh bar times b minus kh bar minus h bar. But both of these are actually the eigenvalues of the same operator j square. So you can equate these two eigenvalues because both are eigenvalues of j square, so they should be same. But let us see the eigenvalue equation of the operator j square. We have written it here in this equation A5, that this is j square ket psi equal to a ket psi. So you have assumed that a is the eigenvalue of the operator j square. So you can write that this eigenvalue defined in equation 3 and this eigenvalue defined in equation 4, both will be equal and both will be equal to a. So we can write here, therefore a, which we have assumed that it is the eigenvalue of j square, that can be written as this is equal to b plus lh bar times b plus lh bar plus lh bar. So plus lh bar plus lh bar, and this will be equal to this much. See here, this is b minus kh bar times b minus kh bar minus h bar, and say this is equation 5. Actually, when you will simplify this equation 5, then you can get the value of b. I am not doing the algebra, you can try yourself. So you can say this gives, this is just an elementary mathematics, so I am not doing that. But from this equation you can easily see that this b is equal to h cross over 2 times k minus l. You will see. Do the algebra yourself and you will get this result. And once you have obtained the value of b, then using this equation 5, you can obtain the value of this a. So you can say, so from equation 5 we get, I am not doing again the algebra, this is just an elementary mathematics you can do. You will find that a is equal to h bar square times k plus l over 2 times k plus l over 2 and plus L. You can see. Now let us consider that this k plus L over 2 is equal to j. So let us take, sorry, here there will be 1 in fact. This is 1, not L. I have written it directly, so remember this will be 1. This is 1. Now let us take this k plus L by 2 is equal to j. You can see that this k plus L by 2 which is equal to j, that will be necessarily equal to an integer, and k minus L by 2, this is also an integer, because k and L both are integers, so this is an integer. So k plus L by 2 and k minus L by 2 both will be integer. And so if you assume that k plus L by 2 is equal to j, then from this result you can see what will be a. Therefore you can write a is equal to j times j plus 1 times h bar square. You can easily see it here. This is j, so this is j times j plus 1 times h bar square. Say this is your equation 7. And see this equation number 6, where we have defined this b. So you can say that this b is equal to h bar over 2 times k minus L. Now you can see that since j is equal to k plus L by 2, so what will be the maximum and minimum value of k and L? You can easily define. Since j is equal to k k plus L by 2. So what will be k max? In fact, k max will be equal to 2j when you will take L equal to 0. And k minimum, this will be simply equal to 0. Simply equal to 0. And similarly, if you want to find the maximum and minimum value of this L, that will be also same. So similarly, we can say L max, this will be equal to 2j, and L minimum, this is equal to 0. So you can see here, when actually k will be equal to k max, that is it is equal to 2j, then definitely this L should be minimum. So when k is equal to k max, then L is equal to L minimum. And when k will be equal to k minimum, then L will be equal to L max. You can easily say. So in this way, you can find what will be the values of this B. This B, which is h bar over 2k minus L. So when we will take L equal to minimum, that is 0, and this then k will be maximum, and k maximum is equal to 2j. So taking the minimum value of L and maximum value of k, you can find the maximum value of this B. And similarly, taking the minimum value of this k and maximum value of L, then you can find the minimum value of B. So what will be B minimum? Therefore, B minimum, if you want to find the minimum value of B, how you can obtain from this result? You can see it here. This will be h bar by 2 times, and there is k, but we have to find B minimum, so we should take here k minimum and L maximum. L maximum. And what will be this? You can see here. This will be h bar by 2 times k minimum, you know this is 0, and L maximum is 2j. So this will be equal to minus jh bar. This is actually the minimum value of B. Now in the similar manner, you can find the maximum value of B. What will be this? If you try to find the maximum value of B, what will be the result? This will be h bar by 2 and k max. Now you have to take k max and L minimum. L minimum. And you can see this will be h bar by 2 times k max. You can see here this is 2j. So this will be 2j and L minimum is 0. This is 0. So this will be jh bar. Jh bar. So you can see the value of B, which is actually the eigenvalue of operator jz, that lies between minus jh bar to plus jh bar. Minus jh bar to plus jh bar. So in this way, you can say what will be the different values of j. We have obtained the limiting values, and all the intermediate values between minus jh bar and plus jh bar you can easily find. So the eigenvalue values of JZ are you can say this is not eigenvalue. First of all, write like this. You should say this should be stated like this. Hence, h bar by 2 k minus l have values lying between minus jh bar minus j plus 1 h bar and so on minus h bar 0 h bar 2h bar so on j minus 1h bar and jh bar. You can see these are the different values of h bar by 2 k minus l. And what will be the equation number? Let us say this is 8. Equation 8. So you can see that jz have eigenvalues from minus j to plus j in the units of h bar, and so there are total 2j plus 1 eigenvalues of this operator jz. And so we define this as a quantum number m, where m will be actually all the values 2j plus 1, and actually this m will be called magnetic quantum number. So in this condition you can say that so jz has 2j plus 1 eigenvalues from minus j to plus j. Minus j to plus j. So we define B equal to M, where M have all these 2j plus 1 values. 2j plus 1 values. So finally you can see that the eigenvalue equation of these operators j square and jz can be written like this. You have seen that the eigenvalue of the operator j square is a, and we have obtained that this a is equal to j times j plus 1 h bar square, and so the eigenvalue equation for the operator j square will be what? You know, j square ket psi, this is equal to a ket psi, but you have seen that we have obtained the value of a, so you can write this equation as j square ket psi equal to j times j plus 1 h bar square ket psi. This is actually the eigenvalue equation of the operator j square, And so you can say that this j times j plus 1 h bar square are the eigenvalues of the operator j square. And just we have seen that the eigenvalues of the operator jz, that is simply equal to mh bar, because we have written here that this operator jz has the eigenvalue h bar by 2k minus l, and the values of h bar by 2k minus l are lies between minus jh bar and plus jh bar, and all the values of this j, that is j minus j plus 1, and similarly like this j minus 1 and j, all these are written by a symbol m. So you can say that m is actually equal to what? M equal to minus j minus j plus 1, so on, and j minus 1 and j. Total values are 2j plus 1. So all these numbers are written by the symbol m. So m depends on the value of j, and m for a given value of j, m will have 2j plus 1 values, and those values are actually the quantum, actually those values are actually m, and m is a quantum number which is also called magnetic quantum number. So you can write that the eigenvalues of the operator jz are mh bar. So for the operator jz, you know jz is operated on kth psi, and you get b kth psi. This is eigenvalue equation. But you have seen that this b is equal to h bar by 2k minus l, and the values of h bar by 2k minus l is equal to, in fact, mh bar, where m ranges from minus j to plus j. Total values are 2j plus 1. So you can write jz operated on kth psi is equal to mh bar kth psi. This is actually the eigenvalue equation of the operator jz. So here m is a quantum number which is equal to minus j2 plus j at a step of 1. So total values of m for a given value of j is equal to 2j plus 1. And this quantum number is known as actually magnetic quantum number, and you will see this L is actually known as orbital quantum number. And m is known as magnetic quantum number. This L is also called azimuthal quantum number in accordance with the Sommerfeld theory. Now, in fact, this eigenvector which I have written kth psi, this eigenvector is generally written in terms of the quantum numbers j and m. So in general, kth psi, this state is written by the symbol kth jm, or you may also write like this. This is in fact kth j comma m. You may write this without comma, and you may also write like using the comma. So this eigenstate kth psi of the operators jz and j jz and j square is written by this symbol ket jm or ket j comma m. So finally you can write the eigenvalue equation for these two operators like this: j square ket jm. I would like to write this eigenstate simply by ket jm, not j comma m. Without comma we will write it, and this is equal to j times j plus 1 ket jm, and jz ket jm, this is equal to mh bar ket jm. So these are actually the eigenvalue equation of the operators j square and jz. You can see the eigenstate of both of these operators are ket jm, and their eigenvalues are different. The eigenvalues of operator j square is j times j plus 1, and the eigenvalues of the operator jz, this is actually mh bar. Sorry, j plus jm h bar square. Here there should be h bar square. So h bar square j times j plus 1 ket jm. And so this j into j plus 1 h bar square, these are the eigenvalues of operator j square, and jz has the eigenvalue mh bar. And you have seen that this m depends on the value of j, and for a given value of j there will be 2j plus 1 value of this m, and that m will lie from minus j to plus j. So I hope you have understand the each and every step of the calculation for finding the eigenstate and eigenvalues of these operators j square and jz. So watch the video and try to calculate these eigenvalues of operators by yourself. And when you will watch seriously the video, you will find that this is very interesting and you can easily understand all the concepts.